Alright, so today we're beginning our unit about rational functions. So we're going to be dealing with different rules that you're going to need to write down. The first thing we're going to talk about is the parent function for all rational functions. So the parent function for all rational functions, I'm just going to type in f of x. You could type in y if you want to. Is 1 divided by x. That's your parent function. Now something you need to understand about this parent function, it has two asymptotes. It has a vertical asymptote, and the vertical asymptote is x equals 0, and it has a horizontal asymptote at y equals 0. So the vertical asymptote is right there, the horizontal asymptote is right there. So here we go. There's the horizontal, there's the vertical. All right. So we're going to talk about the rules for horizontal asymptotes and rules for vertical asymptotes. So the first thing we're going to talk about is the rules for vertical asymptotes. All right. So what I'm going to do is I'm going to clear these out. And I'm going to make, right now you can see that if I plugged in a 0 and for x, that would be not good because you can never have a number divided by 0. So if I put minus 5, what number minus 5 is 0? Well, that would be positive 5. Okay? So you can see right here my vertical asymptote is at a positive 5. Now if I were to say x plus 5, what am I going to have to do? I'm going to have to move the asymptote over, and now we're at a, there we go, negative 5. Well, what happens if I put plus 2? Well, got to move it back over here. Okay. All right, let's add something here. Let's add a parentheses. All right, I put a parentheses. Let's do x minus 3. All right, we have actually two asymptotes. We have one at x minus 2, and we have another one at x equals 3. Oh, not s equals 3. X equals 3. There we go. So now you can see we have a vertical asymptote at negative 2 and 3. Why? Because that's the number you would plug in to make equal to 0. So are you telling me if I do another one down here, like x plus 1, now we have 3 vertical asymptotes. So what's my asymptote going to be? X equals negative 1. So we have an asymptote right here, and now way over here. So we have 3 vertical asymptotes. And what's the rule? Whatever you would plug in to make it equal to 0. That's the rule for vertical asymptotes. Now, we're going to talk about removable discontinuity. All right? So what is removable discontinuity? So look what happens right here. Look what happens if I put in x plus 1 up there. Well, all of a sudden now, we don't have a vertical asymptote. What do we have at when x is a negative 1? Let's see if you can see it. When x is a negative 1, it's undefined. I don't know if you can see that, but there's a hole right there. That's called a hole or removable discontinuity. So this might be a good little example for us to talk about. So I'm going to take a picture right here. So in your journal, we're going to write down, you're going to write down f of x equals all of this. Now whenever something cancels out, that is what's called removable discontinuity. Okay? And so we have a removable discontinuity at x equals negative 1. So right here, technically there'd be a hole in the graph right there. But we have 2 vertical asymptotes. Okay? We have a vertical asymptote at x equals negative 2, and we have a vertical asymptote at x equals 3. Because if I plug in a negative 2 right there, and I plug in a 3 right there, it makes the denominator equal to 0. So how do we find vertical asymptotes? Whatever makes the denominator equal to 0, but sometimes some factors cancel each other out, and that's where a removable discontinuity happens. Well, what happens, let's see here, what happens if we happen to have like x plus 1 twice? Like we have x plus 1 twice. All right, let's check this out. Now, would you agree that right here, these would cancel each other out. But wait a second, you have one left. So do you have a whole or removable discontinuity, or do you have a vertical asymptote? Well, let's check. If we have a vertical asymptote, we should see it, x equals -1. There we go. There's the vertical asymptote. So we don't have a whole. Even though these cancel out, we don't have a whole. We have a vertical asymptote. Now, what is an asymptote? An asymptote is a line of like it's infinite. Well, guess what it has along the line? A whole bunch of points. So even though we have removable discontinuity at -1, there's an asymptote. So because an asymptote's full of holes. So that's why the asymptote basically trumps the fact that these cancel out. So that's what you got to be careful of. Now, obviously, if there wasn't any there, if it was just x plus 1 and x plus 1, you'll see you have a whole, not a vertical asymptote. There's only one vertical asymptote. That's at -2 right there. You can see it. And now we have a whole at -1, which would be right there. Oh, there you can see it. There's the hole in the graph. If you see where my arrow is, there's an empty space right there. It's a hole. It's undefined. Okay. So what we're going to talk about now is a little bit different rule, and this rule goes for what's called horizontal asymptote. So if you would, we're going to write rules for horizontal asymptote. All right. All right. So horizontal asymptote rules. All right. We're going to do with rule number 1 for horizontal asymptotes. All right. Now let's pretend we have a function, any function. I'm just going to call it f of x. And that equals a times x to the power of m plus I don't care. And that's being divided by b times x to the power of n plus I don't care. So basically all I'm worried about is what this power is and what this power is. That's all I'm worried about. So there's 3 rules. If the power is greater than n, then there's going to be no horizontal asymptote. Okay, there's going to be no horizontal asymptote. Now I'm going to give you an example. I'm just going to tell you. I'm going to show you. Well, let's pretend the function was f of x equals 3x cubed plus 2x squared minus 1. And that's being divided by, let's say, 5x squared minus 2. Can you see that this power is greater than this power? My 3 is greater than the 2. So I have no horizontal asymptotes. If it asks me for a horizontal asymptote, I'll say it's got none. Now I'm going to go ahead and graph this so you guys can see that it's not going to have a horizontal asymptote. So I'll go back over here. Let's type in f of x equals. I make a little division bar. There we go. So I believe I said, what, 3x cubed plus 2x squared minus 1. All right, see if I can remember. 3x cubed minus 2x squared. Was it minus 1? Oh, plus 2x squared minus 1. Really, it really doesn't matter, but I'm just going to make sure I get it right here. All right, now it's all being divided by 5x squared. 5x squared minus 2. Minus 2. Now, if you're wondering what a horizontal asymptote, it's a line that runs horizontally. You'll notice it does have what's called a slant asymptote right here, but that's not a horizontal, that's a slant asymptote. And it does have a couple of vertical asymptotes running down, but it has no horizontal asymptote. That's if this number right here is bigger than this number. Okay? There's not a horizontal asymptote. Okay? So, anything where this number is higher, there's not going to be 1. Alright? So there's no horizontal asymptote. So, let me go back to rule number 2. Number 2. if m is less than n, then the horizontal asymptote will be at y equals 0. So let's go ahead and change things around. If f of x equals, let's say, I'll go ahead and switch it. I'll put 3x squared plus 2x minus 1, and then I'll make the bottom exponent right here bigger. Okay, so I want you to see that all I'm doing is I'm using the same numbers, except I'm changing the powers. This is where the horizontal asymptote will be at y equals 0. So I'll just use the same graph. I'll make that a 2. I'll make this a 1. There we go, and I'll make this a 3. And hold on, I'm going to make it. So I'll put a 2. There we go. That'll work. Now what I want you to understand is we have a horizontal asymptote at y equals 0. Now what does that mean? That means this graph gets really close to 0. Now it looks like it does cross over here and it does cross over here, but if you zoom in, you can see that even after it passes through, what does it want to do? It wants to get back towards that asymptote. And the reason why it's at 0 is because this power is less than this power. So for example, I put a 1, it's still going to be 0. If I put a 5, it's going to change it. It's going to change it to no horizontal asymptote unless I put, say, a 6 there, and then it gets back to 0. And look at the end behavior. The asymptote, you're looking at the end behavior as it goes forever to positive infinity and negative infinity. So that's rule number 2. Okay? So if it's greater, what do we have? We have none. If it's less, we have y equals 0. So we have the third rule. What happens if they're equal? So number 3. What happens if m is equal to n? So let's go ahead. Let's go ahead and make one here. Ready? F of x equals, let's say, 8x squared minus 2x plus 5 over 2x squared plus 1. Can you see that these powers are the same? 2 is equal to 2. If that's the case, then your horizontal asymptote will be whatever a divided by, not a times b, a divided by b is. So if I go up here, like what's a over b? This number over this number. A over b. What's our a and b value? 8 over 2. So in this one, our answer is going to be 8 divided by 2, which is equal to 4. And that will be our horizontal asymptote. Let's check it out. Ready? Do one more. So we have divided by, and we have 8x to the power of 2. I put what? Minus 2x plus 5? Just randomly minus 2x plus 5. And then right here we have 2x squared plus 1. If you're wondering where I'm getting numbers, it's like I'm just making stuff up as I go along, but the main numbers I want you to understand is the fact that these numbers are the same. The 2 and these powers are the same. So I know my horizontal asymptote is going to be at y equals 4. Hopefully you can see how this graph gets close to the 4 on both sides. All right, now that we have some ideas of what we're looking for, what we're going to do is we're going to go over these first 3 problems. Okay, it says find the domain of each function and the equations of the vertical or horizontal asymptotes, if any, and use interval notation for the domain. Now, first thing we're going to do is we're going to find the asymptotes, because the asymptotes control whether or not what our domain is. So for example, all right, if I just go back to our, let's go back to our parent function, okay, which is 1 over x. All right, so if I just go to our parent function, which is 1 over x, we have 2 asymptotes. We have x equals 0, right, which is our vertical asymptote, and we have y equals 0. And if you're wondering why, let's see here, take a picture of that. If you're wondering why the horizontal asymptote's at y equals 0, because technically I could say 1 times x to the power of 0 over x to the power of 1, and it follows the rule where if we have m over n, m is less than n, so therefore our horizontal asymptote is y equals 0. But if we want to talk about the domain, all right, you can clearly see that the domain goes from here, and then it gets really close to 0, and then on the other side of the 0. So how would we write the domain? It's coming from negative infinity, and it's traveling to 0. And then over here, we're going from 0 to positive infinity. Okay? But the domain, how would we write the domain? The domain would be from negative infinity to 0 union with 0 to infinity. That's how you would write the domain in interval notation. We have to use this little u, this union symbol, to be able to combine this side with this side. So that's what we're going to be talking about when we're dealing with our domain. So we have some asymptotes we have to worry about. All right. So even though you can't see it, I'm going to put x to the power of 0. So we have m is less than n. So we have a horizontal asymptote. I'm going to put HA at y equals 0. So we have a horizontal asymptote at y equals 0. But the vertical asymptote, we have none. Now, why don't we have a vertical asymptote? Well, because there's no number I can plug in right there that when added to a 1 makes it equal to 0. Because a negative times a negative is a positive, all right? And a positive times a positive is still a positive. Even if I put 0 there, it's still 0 plus 1. So the domain, there's no vertical asymptote. So that means our domain is literally going to run from negative infinity to positive infinity, where there's nothing to slow us down. All right. So if you're not sure what I'm talking about, let's quickly make a graph here, and I'll put 4 over x squared plus 1. And like I said, there's a horizontal asymptote at y equals 0 right here, but you can clearly see that even if I zoom out, it goes forever to the left and forever to the right. So the domain is negative infinity to positive infinity. Let's look at the next one. All right, so the next one, what's the domain? What are the asymptotes? Let's start with the asymptotes. We have a horizontal asymptote, and we have a vertical asymptote. All right, our horizontal asymptote, does everybody see at this power? That's a 1 and that's a 1, so these are the same power. So it's going to be A over B. So our A value is 2. Our B value is 1. So 2 over 1 is 2. We have a horizontal asymptote at 2. But we also have a vertical asymptote. The reason we have a vertical asymptote is because there's a number I can plug in here to make it equal 0. And that number is, I apologize, I should put y equals 2. And our vertical asymptote is at x equals negative 1. All right, so negative 1 plus 1 is 0. So that's our vertical asymptote. All right, now our domain, we have a restriction here on our domain. All right, x cannot equal a negative 1. So what we're going to do is we're going to say it goes from negative infinity all the way to negative 1. We're going to union that, okay, union with negative 1 to infinity. All right. So what would that look like? All right, let's go ahead and type it into Desmos, show you what it looks like. There we go. Now I told you there was a horizontal asymptote at y equals 2. There it is. I'll change the color so you can see the difference. There we go. And I said there's a horizontal or vertical asymptote at x equals negative 1. There we go. All right, so that you can see that it goes from negative infinity to negative 1, and then from negative 1 to positive infinity, and that's why we write it like this. All right, last one, number 3. Let's talk about the horizontal asymptote, and let's talk about the vertical asymptote. All right, so even though you can't see it, that is x to the power of x plus 3 to the power of 1. All right, and so over here, if I multiply those together, you'd get x squared. 1 minus 2 is negative 1, so negative x. 1 times negative 2 is negative 2. So this would be the expanded form. If you multiply those together, you can clearly see this is to the power of 1 right here. And this is to the power of 2. So our horizontal asymptote, once again, is at y equals 0. our vertical asymptote, there's two numbers that we could plug in, -1 and a 2. So I have two vertical asymptotes. I have one at x equals -1 and one at x equals 2. So I have two vertical asymptotes. So that's going to really mess up our domain. Okay, so let's take a look at it. Ready? So let's clear that out, clear that out. Look at our problem, x plus 3. What was our problem? Oh, x minus 2, not x minus 3. There we go. All right, so we've got a couple of vertical asymptotes at x equals -1, and we have one at x equals 2, and we have a horizontal asymptote at y equals 0 right there. All right, you can kind of see all those. Now, check this out. We have three different domains here. We got to all put, we got to union together. So we have -infinity to -1. We have from -1 to +2. And then here we've got from +2 to infinity. So we got to like write each of these sections. All right. So I'll say it once again. Ready? So we have from -infinity to -1 right here. Right here in this section we have from, let's see here, -1 to +2. And then right over here, that's this section right in there. And then over here we have from 2 to infinity. So we have 1, 2, 3 sections. So here we go. How do we write that? Let's go. Let's check it out. All right. So our domain goes from -infinity to -1 union with -1 to 2. And it's not equal to. That's why it's soft bracket. It's not equal to. Union with 2 to infinity. Got to fit that all in there. But that's the domain for number 3. All right. So now that we're done with that, let's move on down and we'll talk about what's called a slant asymptote. Okay. We have a slant asymptote. So let's check this out. We've got 5x squared minus 10x plus 1 all over x minus 2. So what I want you to do is right now in your journal, I want you to write this out. Okay? So you can see that this power is bigger than this power, therefore there is no horizontal asymptote, but we do have a slant asymptote. So there's rules for slant asymptotes. So I'm going to put slant asymptote. Now, slant asymptotes are also called oblique asymptotes. All right? So here's the rule. If I'm going to put in f of x equals a times x to the power of m plus I don't care over b times x to the power of n plus I don't care. Which I don't care means it doesn't matter what follows it, okay? You're looking for your highest exponent right here, your highest exponents. If m is greater than n by, here's the key thing, by 1 degree, not 2 degrees, not 3 degrees, not 4 degrees, just by 1 degree, it has a slant asymptote. Okay, so you will find it. So let's take a look at our situation here. 5x squared minus 10x plus 1 all over it. See, that's 1 degree. I'll show you how to find the slant asymptote. Here we go. We're going to take 5x squared minus 10x plus 1. And we are going to divide it by x minus 2. Now there's two ways to do this. Being that this is a linear factor right here, we can actually use synthetic division and do it a lot faster. So I'm just going to go ahead and do it. Or you could do long division if you want to. Okay. So we're going to list our x squared. We're going to list our x to the first and x to the 0. And right here, if that says x minus 2, I'm going to put a positive 2. How many x squareds do I have? A total of 5. I have negative 10 x to the power of 1s. And I got 1 constant. And then we just work our way through. Ready? Bring down the 5. Just remember, if that says x minus 2, you got to plug in a positive 2. 2 times 5 is 10. Add them together, you get 0. 2 times 0 is 0. Plus 1 is 1. We have a remainder of 1. We don't care. In this particular situation, you don't have to worry about the remainder. You just worry about what's called the quotient. All right? This is your x to the first. This is your x to the 0. You never worry about the remainder, just what these two numbers are. Okay? Or whatever you have, you don't worry about the remainder. Okay? So check this out. This is going to be 5x plus 0, which is 5x. What does that mean? We have a slant asymptote at y equals 5x. That's our slanted asymptote. Now I'm going to let you know what it looks like so you can kind of visualize it. Okay? So here we go. I'm going to go take that out, take that out, take that out. All right? Over here. Okay, I'll go ahead and do divided by. I'll type in 5x squared minus 10x plus 1. And I'll go over x minus 2. All right, I know it's kind of hard to see here. Okay, I'm going to zoom out just a bit. All right, so you see this graph right here? We do have a vertical asymptote at x equals 2. So we have a vertical asymptote. Go ahead and change the color. Let's make it black so you can, or purple, there we go. We have a slant asymptote, y equals 5x. You see how that creates those boundaries? I'm going to go ahead and zoom in, all right? Hopefully you can see it. You see how that slant asymptote gets really, really, really close to that side, and this vertical asymptote gets close to the other side? That's called a slanted asymptote, right? Right there. That's our slant asymptote, y equals 5x. All right? So that will only work if and only if this is 1 degree higher. So I'll do one more here. I'll do one more. I'll do number 5. We'll find the slant asymptote for number 5. Okay? So here we go. If I have, I'll go ahead and do the synthetic division right over here. All right? The only reason I'm doing synthetic division because this is a linear factor and that's not raised to the power of 3 and that's a 4. But it always has to be 1 degree higher. So here we go. X squared, x to the first, and we have a what? X to the power of 0. How many x squareds do we have? 1. How many x to the firsts? 1. We have negative 6 right here. If that says plus 1, I got to use a minus 1. We'll do a little synthetic division here. Bring down the 1, multiply, you get negative 1, add it together. Well, that works out nice and neat again. Negative 1 times 0 is 0, and we got a remainder of negative 6, but I don't care. I'm only worried about these. So my slant asymptote is actually going to be y equals x. All right? And my vertical asymptote is going to be at a negative 1. So if I wanted to graph this, if I just wanted to graph it nice and neat, I would make a vertical asymptote right here at negative 1 right there. It's kind of, I didn't do a very good job. I'll try a better job here. That's not bad. Okay? And then check this out. I'm going to make a slant asymptote known as y equals x, which basically goes from here all the way through. All right? And so my graph is going to be right in here. All right? It's going to be right in here. So check it out. We know our new slant asymptote is going to be y equals x right there. And we know that was going to be a negative 1. So I'll create that, and I'll put x squared minus x minus 6, and it's going to be all over x plus 1. I'm going to hit home so we can see it. All right? Hey, look. Oh, it's supposed to be plus x. My bad. There we go. There we go. That's much better. All right, cool. Check that out. All right. Well, I was mistaken. You can still see that it's going to be on the outside. Very nice. It's going to be on the outside, not on the inside that our last one was. It's going to be on the outside. So negative 3, 0, and 2, 0. So what would I do on my graph? I would put one negative 1, 2, 3, 0 right here. And I'd put over here at 2, 0. There's a couple of points, and it's going to be on the outside. My apologies. All right, and we also have one at 0, negative 6. All right. So 0, negative 1, 2, 3, 4, 5, 6 are right here. So this is going to come, and it's just going to hit that line and go that way, and then this is going to come down here and hit that point right in there. Didn't do a very good job. It's not exactly easy to sketch on this board, okay? But you can kind of see what it looks like. But it's always important to know how to find your slant asymptote and your vertical asymptote. So what's the rule for slant asymptotes? Once again, let's go back and take a look at it. If they are 1 degree above it. So this has to be 1 degree higher. All right, and that's it. All right. So that's going to be the rules for today. All right, and you can talk about intercepts in the domain. You can try to fill those in. There were no holes in these graphs. There was no holes. There are intercepts like the y-intercept and the x-intercept. So that's basically the video for today. All right, and we'll continue on tomorrow.